Joining here, John, software engineer with 10 years of experience. I'm the lead maintainer of Latterly.io. Latterly helps you land your first or next software engineering role. You can sign up for free and unlock cool stuff starting at $1. Here's the community tab. You can join the Discord network, get your questions answered either there on the Discord or drop a comment here. And we're just kicking off. Part of your interview prep is Leetcode. So that's what we're doing Monday through Friday at 3 p.m. Eastern these days. And before I get into that, I want to spend 5 minutes talking about what's coming soon for stream content, as well as Latterly roadmap and website updates. We'll just do 5 minutes here and then we'll get into the Leetcode. Before we kick off, tap the video, give it some likes. That'll help the algorithm send it around so that we can get this video in front of more eyes, educate more people, and grow our community. Okay, so what's coming soon? The most soon thing is like this stream. So in this stream, we're going to do the Leetcode kata, trying to get up to number 6, but we'll time box it into an hour, so we might not get all the way to 6. We'll see. But the goal is to be able to do those first 6 during an hour. And what's coming later today? So later today, I will be enhancing my open source resume tool. So here it is at GitHub, which is Vanderveer/myresume. And the enhancement is going to be creating tags. So I'm getting like asks for like resume customization. And I'm typically not a fan of this because it's not an efficient use of my time. But if I can make a couple tags, like if people are often asking for references, and I can just have a version of my resume that has the references, then that's pretty fast. That's a pretty easy change. So basically, we want to modify the resume Python script. Where is it? Oh yeah, create PDF resume. Want to modify that to where it will consume tags and it can build you like a semi-tailored version. Like it might include the references or it might include the projects section, which is something that's useful for me in some cases if they want to highlight particular skill keywords that are not showing up so much in my experience, then it can be in my projects. And the trade-off there is that my resume is longer. So now it's going to break 2 pages. Usually I don't want to do that, but in some special cases, that'll be okay. So we'll pass the flag and get that version. So that's going to be done later today. I don't know if I'm going to stream it or not, but I'm going to implement that today. Tomorrow I'll be flying to PyCon, so you can follow me on TikTok or YouTube for short video updates. I will not be streaming tomorrow or Friday because I'll be at PyCon. So today's Wednesday, Thursday, Friday. We'll be skipping those. And then here are 7 things we'll be doing later this week. One is that I'm going to make a new custom GPT for interview prep, specifically on the behavioral and sys design, not on coding rounds. Why do I not want to make a coding round GPT? Because there's already an awesome AI coding round bot on interviewing.io. So if you go to interviewing.io, which I highly recommend, if you sign in, there is a tool which is the AI interviewer over there. So you should totally have like a custom GPT for coding round interview, but use theirs. I'm not going to make one. For me, I'm going to make one for behavioral and sys design. This will probably be a paid product in the future, but if you join the Discord now, you can help do the beta testing and you'll get free access for a limited time. Big deal there. I'll really appreciate the feedback so I can make it better. And also I would love to get this into a bunch of people's hands for free. But I can't do that like sustainably forever. So sign up now. In addition to making like the AI tool, I'll also be finishing like my personal tasks that I'll be doing is that later this week, I'll finish up my own behavioral anecdotes. I have them. I have the list now. You might have seen the stream yesterday where I got the list and I got a bunch of the STAR method filled in, but there are still some gaps and then I need to like go through and refine it. So it's all drafted, but I need to refine it. I'll be getting through Kata 6 Whether I do that today or not, that'll be happening this week. And then I'll have a reversal decision. The reversal decision works like this. It's really hard to get all the way past 6 given an hour time box. So maybe what I should do is alternating days work the kata in reverse, where one day I go 1 to 6, next day I go 12 to 7, and alternate that way. At least until I get good at each portion to where they're both independently under an hour or even under 45 minutes. And then I can squish them together if I want to do a longer time box of an hour and a half or 2 hours. But as it stands, I really worry about if I'm going 1 through 6, then 1 through 7, then 1 through 8. It's hard to get sufficient time on that final one, which is supposed to be like the one you're learning that day, right? So that's what I'll be thinking about if I want to take this alternating day reversal approach. Open source contribution, we're going to update laterally, so tune in for that, and we're going to enhance the Stripe integration. If you've signed up for laterally, if you go over here, and if you do one of the paid ones, what you'll notice is that the dollar is not recurring currently. Like you just pay $1 and you get like access forever, which is great for you and it's terrible for me. So the enhancement here is that it's actually a subscription. And there's a second part of the enhancement where the callback works. So currently I have to manually pull a report and see who got updates that day, and I have to like fix it like every day manually. So what I would love to happen is just a real-time Stripe callback where you sign up and you immediately get the permission. You don't have to wait till the next day. So those are the Stripe enhancements. Okay, so with that, let's get over to the Leetcode kata itself. Here you can see this article 3 on the blog. The kata is a list of ordered Leetcode problems that each help us learn an important pattern that is likely to show up during a big tech interview loop. So we start with 2sum. Here's number 167, 2sum 2. The input array is already sorted. So this problem says, given a one-indexed array of integers that we call numbers, where numbers is already sorted in non-decreasing order, let's find 2 numbers such that they add up to a specific target. These 2 numbers are the index 1 of numbers and the index 2 of numbers, where 1 is less than or equal to index 1 and so on. So you'll never have a 0, which makes sense because it's one indexed. And they are asking for us to return the indices of the 2 numbers, again, added by 1 because it's all one indexed, and return them in the form of a list, an integer list, which will always have length 2. Tests are generated so that there is one solution. We don't have to worry about a sad case with no solution. We don't have to worry about duplicates. And there is a requirement that the solution must only use constant space. Great. So given that it's already sorted, using pointers or a window is intuitive. Memory complexity is constant in that case. In the worst case, I need to check every number in numbers, which means worst case time complexity is O of n. How do we decide between a window and numbers? Or sorry, a window and pointers? Really, any 2 pointers will define a window. So it's not really a decision. It's between pointers and a window. It's a decision between a sliding window and then like a non-sliding window. And here we don't want to slide action because we don't want to point at the same index. That's like one of the requirements. Don't point at the same index. We will use pointers and not a sliding window so that we don't point at same index in the left-right result. Okay, so left will be initialized to 0, right will be the far right of numbers, which is going to be the length of numbers minus 1. And they should never cross. If they ever cross, we're just going to be duplicating the same sum. Because if I say, hey, a plus b is 5, and then you reverse them, b plus a is still 5. So anytime those pointers cross, you can just exit. The way I get the current sum is the left index of numbers plus the right index of numbers. And there's a few conditions here. If above, else if below, else, match found, return. Yeah, that's fine. Match found, return. Oh, 1 indexed. So we're going to want to add 1, left plus 1, right plus 1, because the requirement is that we return the 1 indexed indices. So above is a pseudocode. What's the literal? The literal is that cur_sum is greater than target. That's what we mean by above. Cur_sum is less than target is what we mean by below. If current sum is greater than the target, now I want to decrease my sum. The way I decrease my sum is I take my higher number and I reduce it. So I'm moving right to the left. That's how I can move right to the left. And in the inverse case, I move left to the right, which will increase the overall sum. Cool. Great, we've got 2sum done. So now we'll proceed over to 3sum. 3sum states, given an integer array called nums, return all of the triplets, such as I of nums, j of nums, and k of nums, where I, j, k are distinct and they all add to 0. Notice that the solution set must not contain duplicate triplets. So not only are I, j, k, the indices distinct, but also the values are distinct. So there's a double deduplication. And we can see in example 1, which returns a list of 2 triplets. So there could be multiple answers. Example 2 has none. Example 3 has 1. So we need to handle all these cases. There might be no answers. There might be a single or multiple answers. The intuition is to wrap 2sum with an outer index layer. This creates O of n squared time complexity on an already optimal O of n 2sum. This requires sorting, but n log n sort complexity is not a binding constraint. Memory is constant /O1 because we just use pointers. So let's start by sorting nums. Initialize left to 0. I want to call this outer left to distinguish it from my 2sum left. And I'll say while outer left is in bounds. We want to get the complement, call 2sum, and fast forward duplicates. Then we'll eventually return results. So let's define results. Results is a set, and we want to use set for auto deduplication of tuple triplets. They need to be tuples, not lists, because lists in Python are not hashable and they are mutable. So we want to use tuples in the case of Python. In your other language, you could maybe use an array or a list, something like that. Okay, so the complement is going to be the opposite of the outer left index of nums. That's just what the complement means by definition, by construction. It means the thing which sums it to 0. So that thing which sums any number to 0 will be its opposite. So 1 plus minus 1 and so on. So the complement of outer left of nums is the opposite of outer left of nums. Now we'll call self.toSum. We want to pass it outer left results, the complement. What else do we want to pass it? Nums, it needs nums. Is that enough data so that you can calculate the inner two sum? So the inner two sum, it needs left, right, the overall index, the result set, and the target. I think we have it. Okay. So the complement will be the target. The complement will be the target, and then we'll fast forward as long as the complement is unchanged. There's no sense calling two sum again. It's just a bunch of duplicate calculations. So we'll say while foo, we will increment the outer left. So foo is our like fast forward condition. We want to do this under two sub conditions. One is that we're allowed to because we're in bounds, which is just reproducing this condition. So like while we're allowed to because we're in bounds, then we might fast forward. The way that we distinguish between the maybe yes and maybe no sub cases is this secondary expression, which is like our cache bust. So we're going to compare it to complement. So we're going to compare it to complement in a way that's guaranteed to hit once, just by definition, by assignment. So that's always going to increment outer left. And then it might increment it more times. If I have like a case like 0, 0, 0, 1, 1, 1, 2, 2, 2, you can see how the complement is unchanged even though outer left has increased. So that is the point of this secondary condition. It's like a cache busting condition. Does that make sense? Great. Okay. So that's pretty much it. Now what we got to do is write out our two sum. So we're still on the solution class, so I need self in Python just because it's a class method. And then I'll use the argument list literal from here. Everything's accounted for. One thing I'll do is I'll change the name of complement to target. So the complement is the target, because if we can generate that complement across these two, then adding the third gets us our triplet that adds to 0, which is the requirement. So left here is going to be the outer left plus 1. Right will be the same length of nums. Minus 1, that's the boundary of the array length. And we'll have our standard two sum exit condition. Make sure those pointers don't cross. And we'll do our standard logic where we get the current sum. And there's 3 possibilities of the current sum relative to the target. You could be above, below, or at. In this case, when we find a match, we don't just return, we want to append or add to the result set. So we'll add something called sorted tuple, and then we'll define the sorted tuple as the opposite of the target, which is always going to be the first value, the furthest left value, because the opposite of the target is the value of outer left in nums by construction. Does that make sense? So that will always be left of the left value, which will always be left of the right value. So we don't need to actually call sort. It is sorted, but it's sorted predictably. We don't need to have a call on sort. And then we'll fast forward. You could use left or right. I'll use left arbitrarily just to keep the whole mental model that we're progressing from left to right. And the conditions are analogous. We want a boundary condition and then a cache busting condition. So the boundary condition is from the while loop. The cache busting condition is, in this case, it's my left. Since I'm doing left, it means my left value didn't change. If my left value didn't change, then we know that the complement, the right value, which we'll add to the complement to add to 0, also didn't change. Because the complement, like in a single call to toSum, the target is held constant. So if the target is held constant and the left value is held constant, there can be no other proper right value. It will always be a duplicate. Because we're just dealing with addition here, right? So if we know it's just going to make a duplicate, like even if I find one, it's going to make a duplicate, then why am I running through compute cycles? I can just skip it. So here is our boundary condition, and this left val is our cache busting condition. So we want to see if the left val is still equal to left of nums after we increment. Guaranteed to hit once, and then it might hit more times. Cool, I think this is looking good. We'll work backwards and solve up another a couple other gaps. So above is a pseudocode, cursum is above target, and then here cursum is below target, okay? And then left val is the left of nums, and right val is the right value in nums. So if I'm over, I want to decrease by decrementing right, and if I'm under, I want to increase by incrementing left. Cool. Great, so we have our toSum solved. We're at the 22-minute mark. I think I started toSum at like the 8-minute mark, so 15 minutes between the two is pretty good. I might be being a bit hasty, to be honest with you. We want to try to emulate a real interview format. So being too fast is actually an anti-pattern. Making sure we're reading through the problem. In a real interview, I would be clarifying questions that I have. Some of the questions that I would have involve the return type, the provided data type, the sort, the allowability of various characters, like are they always alphanumeric? There's an interesting constraint down here, less than or equal to 0. So a 0-length string is possible. That's one of those things that you would want to double check in your interview. Will there ever be a 0-length string? Or can I assume that there will always be a populated string? So now we're on to the third problem, longest substring without repeating characters. Given a string S, let's find the length of the longest substring without repeating characters. So intuitively, the limit of the substring length without repeating characters is the same as the limit of the substring length with repeating characters. It's just the length of the whole string. The limit in length of any substring is the length of the string itself. So in the worst case, I need to visit every char in S. So worst case, time complexity must be O of n. So the trick here is, like, the time complexity here is really easy to calculate. All of the trick has to do with the memory complexity. So the naive approach here, I'm checking for uniqueness. A naive approach is to use a scene map pattern or a cache of letters already seen. That would take O in memory in the worst case. Because if I have really it's O of n minus 1, but asymptotically it's O of n. Because if I have a word that's like many unique characters and I need to check the very last character if it was seen anywhere before, I need to have a store of all those other characters, which is O n minus 1. But it's asymptotically O of n. Make sense? Jason, thanks for the likes. So can we beat that? If so, it would need to be a O log n or O1 process. It would seem to be an O log n or O1 process. O1 processes often include pointers and windows. Bazinga! Yes, we can do something here with a sliding window. So with 2 pointers, I can establish a sliding window as opposed to the 2-sum, 3-sum approach of a boundary window that's like a collapsing boundary window or a deflating boundary window. In this case, a sliding window, both pointers will init to a single location, and they will move in some direction at a potentially differential rate. It could be the same rate. If it's just like 0, then the longest substring is just like 1, which is potentially the case. There's an example of that in example 2. You got to move the left and right pointers every time, which is kind of like a limiting case, but you can also see the opposite limit is that left never moves and right just grows across the way. So those are the opposite possible sliding windows. In either case, we will start left and right both at 0. And then we will have like the I longest substring length, which is also going to initially be 0. What else do we need? That's about it. So while foo, do something, and then return I longest substring length. I like this pseudocode structure because I can kind of like jump in and fix the bits I know how to do and leave the hard parts for last. So here, while something is going on, I'm going to do something. Well, what am I going to do? I'm going to do whatever it is that calculates this number. So I can take a working backwards approach. This number will just be the max of whatever it was previously and the new length. So what is the new length? It's going to be the length of cur validated substring. So you see how I'm working backwards? Now I'm going to have cur validated substring is, how do I do this? I don't know, but that's what I need to find next. So it will be left to right because I have a sliding window. So it's just going to be whatever that length is. So instead of this approach, I'm going to say right minus left plus 1. That's how I can get the length without even knowing the string itself. I can just know the length of the string. It's wherever my right pointer is minus my left pointer. And then if they're both pointing at 2, you have a length 1, right? It's not a length 0 if they're both pointing at that letter. So you adjust the off by 1. So now I just need to make sure that I deal with my right hand and my left hand properly. Well, my right hand should be iterating every time. I'm moving my right hand every time. That means that I should do a 4 in range. Okay, so I'm moving my right hand at every iteration. It's going to tick, tick, tick. And then the question is, what happens with left? Okay. And just kidding. even with pointers, I need a distinct cache map. For cases like A, B, A, B, A, for cases like that, where the duplicate is not off by 1 on left or right. Maybe this is clear if I do A, B, B. So you see how if I'm ticking, and I run into a duplicate, there's no way with a singular pointer to track that. Even doing a third B is maybe, doing a C is going to be even more interesting. ABC, ABC, A, yeah. So you might think, oh, you have right, left, and then you also have a previous pointer. Well, what you find out if you look at A and then ABA and then ABCBA, what you discover is you need in pointers. You can't just get away with a priv. You'll need a priv, and then you'll need a 2-step priv and a 3-step priv. And you actually end up, in the general case, needing an n-step priv, which is an n-wise cache anyway. It's just a really, really ugly, non-ascribable way. Like I cannot write n pointers. I can't do it. So it's just a non-ascribable way of doing a scene map. So really just do a scene map. So we did a proof by example there. Is it map in Python? We're going to do a set. The map would just be a dictionary, but we'll do a set. Okay. So we want to know if it's like has duplicate or like is duplicate. So now we know if it's a duplicate. So if it's a duplicate on right, so I'm like BAA. Well, what do I do now? I need to move my left until the duplicate condition is eliminated. I can't move my right back because if I move my right back and then I go forward, I'm just like in a cycle. So I need to move left up until right is no longer a duplicate. Then we'll need to recalculate after we. Ooh. I think this is still correct. We'll need to move left up and then we'll need to recalculate, okay? So if it is a duplicate, we want to move left up. So let's say left plus equals, I called it left, right? Yeah, it's just a, and I could call it left IDX if I wanted it to be clear that it's an index. So we move left up and then we want to scene.remove the left of S. So ABB, I remove the A, okay? And then at the second iteration, I remove the B. You might say, well, they're both pointing at B. How can you remove the B from scene? Because we will add scene afterwards. We will add scene afterwards. So we're adding the right of S. So what do we think about this? Left, right, longest substring, see what I see. I'm moving my right hand on every iteration through S. Is it a duplicate? Yes, it's a duplicate. Okay, well then I need to bring left with me. In the limiting case, they're both pointing at the far right character, which is never duplicated. Okay, here's a weird condition. What if I try to remove a character I've never seen before? That should never happen. That should never happen. Famous last words. Okay, we'll test it and see. New length right minus left. All right, let's see. Wrong answer. Boo. My should never happen was wrong, wasn't it? So what's going on here? Is duplicate right and seen? Oh, because right is a number. That's not the right thing to do at all. Is duplicate should say right of S and seen. We want to get the letter, not the number. Here we're still wrong. Bummerville. Output is 4 when we expect 3. How did I get to 4? Let's print this substring. Let me say cur char is S of right. We're just repeating that a few times. So here we'll clean it up. And then I will log it. So I have P1, makes sense. W2, makes sense. And then another W, and it's still 2. That's where the problem is. That second W should snap. Second W should snap the length down to 1 because it should only have both pointers on the W. Okay, so we can see the issue here. If is duplicate should be while is duplicate. That I was way more confident that that was going to fix it. Okay, so this makes sense, and now I'm on the second W. So my left goes up to 1, okay? And I remove cur char. Well, that's the wrong thing to remove. I should remove the left of S. Wow. So many improvements, still so bad. P1, W2, W2. So I move my right, and now I'm on the W2. That's good. And now I have another W. So my left comes up 1, and I remove P from seen. Then my left comes up another 1, and I remove W from seen. Key error is B. How are we hitting this B? This is interesting. A, B, it's all the way down here. So it's the second B. C, B, A, B, C, A, B. A, B, C, A, B. So B is seen. B is seen. So I have to move my left up, okay? And now I'm removing the B. It's acting like it's never been seen before. Oh, no, okay. That was not the case. I had to view more logs. CBB. So it's on this B down here, CBB. So my left gets to C. Now my left gets to B. It still doesn't error. The second time it hits B. Why is it hitting it another time? Left is less than right. Okay, well that eliminated the error, but it's still wrong. Oh, is the issue that I'm eagerly incrementing? I think I might be doing this in the wrong order. So first, let's remove left. Then we'll increment it after. Okay. Okay. All right. Well, that fixed it. So we need to make sure we remove the current left and only increment left after we purge that. I was eagerly purging the next character that it shouldn't have even been pointing at yet. So that was the issue. Now that I fixed that, do I need this bit? Hey, that's even better. If you want, you could like do this. You could do that if you want. I like naming the variable, but that's just kind of opinion. All right, that took a few minutes longer than I would have liked, but hey, here we are. We're at the 42-minute mark. That was longest. Which one was this? Longest substring? Yeah. So now we'll move on to linked list cycle. And we're presented with the following problem. You're given head, which is the head of a linked list. And you got to determine, I don't, this is you. I hope you're ready. Hope you're ready to code. Hope you're ready to give me the answer, chat. By the way, tap like on the video if you're enjoying the video so the algorithm will send it around. Thank you so much for being here. You can also sign up for free at ladderly.io if you're interested in learning more about the problem-solving patterns involved in the kata or programming in general, projects, or whatever it is. You can join the Discord, and if I don't get to your question during the stream, you can come by and chat afterwards. There's also a 24/7 available custom GPT. So what if you don't want to wait for my answer? You can just go ask the GPT. So we're given this head of a linked list. We can see from the type definition on the right hand, this is a singly linked list where I have next. I don't have a backwards pointer. I don't have a priv, right? So the head of a singly linked list, and we need to determine if the list as a whole has a cycle in it. Cycle is just like an infinite loop. So basically, if I keep traversing next, if I ever terminate, if I ever get out, then there's not a cycle. There's not an infinite loop. There is a terminal node. But if I go down the list, boom, and then I hit nodes that I've already seen, it means there is a linked list cycle. And that's in example 1 here. We can see it kind of is giving them IDs, kind of. It says 320 - 4, but you can kind of think of those as like node IDs. And it's like, oh, we hit 2 again. We're hitting 2 over and over. Boom, boom, boom. There's an infinite loop. There's a cycle. There's a problem. And what do I want to return in that case? If there is a cycle, return true. And if there's not, return false. Okay? So if with cycle, return true, and then we'll return false down here. Easy. That's a pseudocode, but that's basically the approach. Here, in the worst case, we have like infinite time complexity. If we just traverse the list linearly, we could have infinite complexity. So we can list the scene, or we can cache the scene node IDs, and then the worst case time complexity is O of 2n minus 1, which is asymptotically O of n. And the reason for that is, in the worst case, let's say I have 10 nodes and the cycle's on the very last one. I have to traverse all the way to the last node, then figure out that there's a cycle. Nope, that would not be the worst case. I have to traverse all the way to the last node. So maybe it's n plus 1. O of n plus 1. I have to traverse all the way to the last node and one more step, and then I figure out that there's a cycle. I think that's right. So the worst case time complexity is O of n plus 1, which is asymptotically O of n. And then space complexity is O of n. Can we beat this? To beat O of n, we typically need to sort and or point. We can't sort without making a copy. So that's out. Code force is better. The questions are harder. What's up, you good? Good to see you again. Yeah, the optimality condition is not asking the hardest possible questions. It is reflecting on those patterns which are likely to be asked in a big tech coding round and making sure that you can deliver the answer and communicate the answer properly, as well as your reasoning for the answer. So the purpose of the kata is absolutely emphatically not to be as difficult as possible. That is a anti-pattern, actually. What you do when you make problems that are as difficult as possible is you fail. And if you think you made them as difficult as possible and then you pass, you in fact did not make them as difficult as possible, I assure you. So we can't sort without making a copy, so that's out. What about the pointers thing? On pointers, we can't traverse to end without we can't traverse back from end. In O of 1, but you could do it O of 2n. So yeah, maybe there is a way to traverse backwards to solve this problem. Maybe there is a way. You can't traverse back without, but you can't do it without adding like a priv on the nodes or making a copy. We can't traverse back without copying. But we can use staggered pointers without copying. In that case, a collision means there was a loop. Memory is constant. So if I stagger my pointers, and if they're moving at different speeds, okay, so they're not index staggered. They are like differential. They're like fast and slow. They're not placed in different places. That would be like an index literal stagger or like a level stagger. They can be pointed to the same place, but they're moving at different rates. So as long as one is faster than the other, if they eventually collide, that means there was a loop. Does that make sense? So with cycle, Baruch says, cool, welcome Baruch. So with cycle is that slow is fast. Okay, so while fast exists, then yeah, if they're pointed at the same place, then that means that there's a cycle. There's a problem here because I'm going to initialize them to both point at head, right? So fast is head, slow is head. So there's a problem where this will just always immediately return true. How do we avoid that? We make the cycle determination after moving fast. So we need to move fast here. Slow is head dot next. Nope, slow is slow dot next. Okay. Slow can do it without any sort of null checking because fast will do it first. So fast will always check ahead of slow. And we need to have null checking on fast. So we say while fast, that's a kind of a null check. We can also say while fast and fast dot next. Right. Fast dot next dot next. That's it. So we need one more, and fast dot next dot next. Do you see why they're called fast and slow? One is moving twice as fast as the other. So this while should be our null checks. Cool. All right, there we go. I don't think I've written it like this before. I really like this because you do all your null checks right there in the while loop. I don't know why I haven't thought of that before. Unless I did and then I forgot it. You never know. You never know. Okay, 52 minutes. Time for the palindrome linked list. Da, 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 da. This is not a 10-minute problem. It says easy. It's easy if you copy it, okay? So yeah, you can copy your palindrome to a string literal or to an array, and then you can check backwards and forwards. You can do that, and that's easy, and it's not efficient. It's not efficient. The hard thing to do is to reverse the second half of the linked list in place. Do I need a proof pointer? I don't know. Because we're dealing with a singly linked list. I think I don't. I think I can flip the second half as a single, and it will disconnect the graphs, but that's okay. Because they don't need to be connected for me to know that the reversed portion of the second half is identical to the first half, which makes it a palindrome. Palindrome is like race car or ABBA. Green beans, like please. What up, green beans? So the problem says, given the head of a singly linked list, let's return true if it's a palindrome or false otherwise. Palindrome is like dad, mom, race car. It's the same forward and backwards. And so here we have a numeric example, 1221, which is true, palindrome, and 12 is false. It's not symmetrical both ways across the middle point. Easy thing to do is make a list copy and compare list to its own reverse. I can do that in 2 minutes, but the problem is that that's not efficient. But that's not efficient. Efficient thing to do is flip the second singly linked half of list, then traverse a lagged pointer in parallel. If first half and second half nodes are value equivalent, and I didn't spell palindrome correctly. performance or like time complexity is O of n, but the space complexity is constant, just 2 pointers. The problem is, how do you code this thing? Okay, so this is a good idea, but how do we code it? I'll say mutator is head, and then I'll say lagged is head. And then I will have list length is 0. Say while mutator. Keep it up, dude. Hemant, thank you. Love from India, thank you. So I'll say while mutator, and we assume no cycles. List length plus equals 1. Okay, so now we have list length and can find midpoint. Midpoint is list length /2. That's the floor math. Okay, so the floor math includes rounding down, which is good in this case. That's the / syntax in Python. It's a floor division. So it's gonna cut it in half and then round it down, which we want in a zero-based system, right? Okay, so now I have a midpoint. So now I can figure out when to flip my mutator. So here I'll say while cur idx. So the mutator went all the way down to the bottom, so we can reuse it. I don't like reusing it. Let's make a counter. Counter node. We'll make a counter node. Okay, so there's the counter node, and the mutator and the lagged will be down here. So while mutator and let's just go with while mutator for now. If the index is less than the midpoint, do something. Else, do something else. We want it to start mutating when it is at or when it crosses. And then here we'll eventually return false. Meaning false means it's not a palindrome. Not a palindrome. I don't know if I'll return true or false down there, but I'll put false for now, and I can change it later if needed. Okay, so if the mutator index is greater than the midpoint, then I want to do mutation. And here I don't want to mutate. I'm not sure about the equals case. So when the current mutator is at the midpoint, we want to think about the 4-length case and the 3-length case. So an odd case and an even case. So in the 3-length case, the midpoint is index 1, right? It's right in the middle. And so when I'm here, if I'm traversing the mutator and the lagged at the same rate, one is from midpoint, one is from the origin top, then the midpoint value will not match to a none. Did that make sense? So you have a 3-length case, you flip the second half, and now you have a disconnected 2-length and a 1-length. They seem asymmetrical. You might say like that can't be a palindrome. But the problem is you have odd palindromes, like DAD is an odd palindrome. So the D matches to the D. What does the A match to? It matches to a none. It matches to a none in Python world, or a null in other languages, or undefined in JavaScript. So you have that null pointer, you have the null pointer or the none pointer. And it is a passage mode, not a failure mode. So let's say I successfully flip my second half. If I successfully flip my second half, now my former midpoint is now the new end node, right? Is it the first node or the end node? DAD is now D none versus DA. DAD is now D none versus DA. So my former A midpoint is now my new end node. You see why this is a tough one? It says easy. But if you do the efficient way, it's not easy. You got to keep a lot of this stuff in your head at the same time. Okay. So D is matching D, A is matching none. So did I flip in the equals case? That's my current question on line 32. In the equals case, what I did is I set A's parent to D. So it's D and DA. So I did flip. I did flip. So we did mutate at the midpoint. In the odd case, and what about the even case? So I don't know, 1, 2, 2, 1, even case palindrome. In that case, you have a length 4, you double divide by 2, and so your midpoint index is going to be 2. So 1, 2, you didn't flip, and then the next is 2. Now you're on index 2, which is a value of 2. That's confusing. Let's deal with the case of 1. Let's deal with the case of 1, 3, 3, 1. Okay, so we did flip on the midpoint index of 2. It might be weird to call it a midpoint. And you might think since it's floor division, the midpoint would go down and you would end up on this left 3. But we're actually on the right 3. We're on the right 3. And so I did mutate their connection because I disconnected the graph. So formerly 3's parent was 3. Now 3's parent is like none. Sorry, now 3's parent is 1 and their child is none. So we did a flip on that midpoint. The counterintuitive thing there is it's not really a midpoint. It's like In the even case, it's the right hand of your symmetry marker between the indices. Okay, well, we're over an hour. So this greater than should be greater than or equals. Let's have GPT finish this up. Roll. You are an expert Leetcoder who is even good at code forces, which is much harder sometimes. Task. Complete this efficient linked list palindrome detection algorithm in Python. Got an interview for a Python AWS Cloud Eng position in 20 minutes. Got 7 years of experience. Wish me luck. I wish you luck, Chris Jones. Hey, hope you'll ping me and let me know how it goes. We can do a bit of a retro if needed. So I'm sure you got this, but if you ever want to chat later, let me know. Okay, so there's the list node. That's fine. Palindrome, if not head or not head dot next. Ooh, okay. That's smart. Wait, if not head dot next, return true. So like 1 is a palindrome, 2 is a palindrome, 3 is a palindrome. I love it. A is a palindrome. The not head thing is weird to me. So none, I guess you could say like none is a palindrome. Yeah, I buy it. None is a palindrome, right? None is symmetrical. It has the same stuff to the left and the right. It's got errors to the left and the right. Okay, so we find the first half. Look, it really changed my code, man. Okay, I was trying to use a counter. Why no counter? Is it using recursion? No, it reverses the list without creating a copy. How does it do this? Oh! You don't need to calculate the midpoint if you have a fast and slow pointer. Dang it, I just got schooled by a robot. Feels bad. Actually, it feels good because the shame will make sure that I remember it next time. Yeah, there's a fast and slow pointer. By the time the fast pointer reaches the end of the list, the slow pointer will be at the midpoint. This technique helps in finding the midpoint, making the solution efficient in O of n time complexity. I mean, I calculated the midpoint in O of n time complexity as well. But they were able to do it with 1 fewer pointers. And even though their asymptotic complexity is the same, the literal wall time is shorter because they're finding it in the first pass where mine is an O2n. Asymptotically O of n, but linearly O2n, right? Later, see ya. Okay, so yeah. The lagged pointer, and I was going to use a lagged pointer, but I was going to use it differently. I was going to get the midpoint and then start a lagged pointer later and then move those at the same rate. So why is it doing differently? The way that it's reversing is the part that I'm not sure about. first half end dot next is reverse the second half. Whoa, that's kind of a mind blown moment. So it has a dual reversal. Find the end of the first half. Okay, so we find the end of this. This is interesting. I like this. So we find the end. I'm gonna like save this. So I can save this as like a solution. So here, first half end. My first half end, yeah, I would call this like the midpoint, but that's fine. First half end. Oh no, this will be the left in the 1331 case. This will be the left 3, not the right 3. So we're on the left 3. And then the second half start is the right 3. That's going to be maybe confusing, but you remember how, like, yeah, in this 1331 case, when we said midpoint, it was the right of the midpoint. But when they say first half end, it's the left of the midpoint. Check whether or not there's a palindrome. So here, and then it's just reverse. So first half end, it makes it seem so easy. I should really remember how to do this because it is like nearly a pseudocode approach. Just like, hey, my second half is the first half end dot next. That's really intuitive. If you can believe that you can build this helper, if you can build the helper properly, then this structure is really intuitive, in my opinion. This is super clean. Okay, trying to let this sink in a little bit. So I know how to get my left midpoint, or the first half end, is I'm using fast and slow pointers. Then I reverse the second half of the list. That's exactly what I wanted to do. It's exactly what I wanted to do. I'm not going to dive into that method just yet, but that was something I was having with when I said mutator. This is like what I'm thinking of. So I'll go look at that in a moment. Now let's just assume that I did it. And your second half start, now I need a pointer to head. Yeah, and this is the parallel traversal I was thinking of. And that means it's a palindrome. So if they are ever different, you return false, except if one of them is none, it's like a free pass. That's like the DAD case. Oh, and then they restore the list. That's cool. Yeah, so it's good to know that even if you want a not mutated version, as long as you're allowed to mutate it and then unmutate it, you can still do it. That's cool. So this all seems really intuitive to me. The trouble is the actual reversing part. And now we're just talking about reversing a linked list. Oh man. I just got trolled. I just got trolled by my own algorithm. I just got trolled by reversing a linked list. Yeah, and once you break up, not gonna lie, the reverse functionality, I didn't get it until I drew it out. It shoves the elements in the back. Yeah, I'm with you, but the thing is that once you break up this problem, at least for me, whenever I'm reading this, I'm like, oh, reverse list. That's like so tricky, right? But then it's like in isolation, you're just reversing a linked list, which is actually like, it's okay. In my opinion, that's actually really easy if you can view it in isolation. I think the problem for me is separating the steps. Like I feel like somehow reversing the second half of a palindrome is way harder than just reversing a linked list, but it's not. Like that's all you're doing, at least at this one step. Cool. All right, let's run it. This makes sense. So now I can see that this structure of this problem, it has like 3 broad steps. We want to do the lagged traversal, find the midpoint. We want to do a pure reversal on the second half. And then we want to do the trivial comparison. It's actually pretty easy if you can just remember the 3 magic steps. The magic words are please and thank you. Please and thank you. Is that 4 words? How do you count those? So if we can remember please and thank you, we can remember the linked list palindrome, right? Maybe I'll give myself that hint without considering that cheating. That could be a terrible mnemonic, but I'm going to go with it. Accepted. Yay, good job. And it's right there in the middle. So that seems like a typical solution. Hey, thanks everyone for being here. We got through what? We got through problem number 5. That's okay. We didn't get to clone graph yet, but we really dug into, I think, the palindrome linked list in a way that I think is really helpful. All right, I hope to see you the next time we do the stream. Remember, we're not doing this tomorrow because I'm flying out to PyCon. So I'll see you Monday.